Hello everyone. I'm going to teach you today on the introduction, basically the introduction to Mohr circle and stress analysis, and we'll be discussing problems, two examples basically on 2D and 3D applications, right? If you know that if any load, any object subjected to a set of loads or moments like that, thus, the internal stressors develop on each any place you will have some internal stresses, right? So if you take an element, so that might subjected to compression and sorry, the tension and compression, likewise shear, right? So due to these compression forces, right? So if you have originally element, right? So let's say uniaxial compression, so your element will be like this after the loading, right? So if you have tensile, right? So your element will be like this, right? It changed the shape, right? Shape of the element, but it depends on the applied magnitude and the shear stresses, right? The shear stresses, right? And change the shape like this. Right. So, but the problem is we need to know what will be the maximum stress, or else the plane where the maximum stress can be found, because this stress depends on the location, right? Within the location, let's say if one plane like this, or else we'll consider a set of planes, right, like this. So there will be acting different stressors on that planes. Let's say the plane is like this, so let's say the normal stress is, so this is from the, how do I draw that? So this is right from the out of plane stress, right? Normal stress, and then in plane stress, shear stress, right? Okay, so you have some stresses like this, and you have to determine on which plane you will have the maximum stresses, and we call it the principal stresses, right? Principal stress. Okay, so the principal stress always mean the plane where the maximum normal stress occurs, and at that plane shear stresses are zero. So if you draw it, the stress with zero, right? Stress on a plane with theta, right? You take some element and apply some stresses, right? So you draw the stress with respect to, let's say like this. Let's say with theta, you will have a variation like this. So if you draw the shear stress, right? If you draw the shear stress, let's say this is the this is sigma normal, okay? So this is sigma normal stress, okay? Uh, stress, or else this is shear stress, okay? Shear stress or sigma, okay? Both axes, both these represent the same axis, okay? So if you draw shear stress, right, you will have something. So here at where the sigma becomes the extreme, right, highest, that it will have 0. Okay, exactly 0. Okay, so and it will come, and again when the sigma becomes negative minimum, it becomes 0, right? Okay, some kind of this variation. So here you can notice this is 0, this is, let's say, sigma 1. So this is the sigma minimum, let's say sigma 2, this is 0, right? So you can see this is the shear stress graph, right? The one I'm boxing are the normal stresses. So you can see when, so if this plane is, let's say this element is rotated like this, right? With theta, your stress varies, right? So with at this angle, your sigma 1 is maximum and shear stress is 0. At that kind of plane, let's say it's this plane, so we call this principal plane, the plane where the shear stresses are 0, right? Here also the shear stress is 0, but sigma 2 is the minimum stress. Okay, so this is the maximum principal stress, this is the minimum principal stress. So both are principal stresses where at on the plane the shear stress is 0, right? So that element is subjected to either pure compression or pure tension, right? No shear stresses on the faces, right? So we need to find that stress, right? So that is the or on other hand, that stress can be uh, used to predict whether that material fails fundamentally, right? So this is the maximum stress on a 2D case we can expect from this material, right? Form in any angle, right? Due to this loading. And this is the minimum stress that we can expect. We don't know, that will happen somewhere, right? That will happen somewhere along some plane. We need to find that. So let's say if we know the uh, compressive capacity of the material and the tensile capacity of the material, right? So we can say, okay, whether our stress exceeds the minimum and maximum, right? So that's one of criteria to determine, right? So that's principal stress criteria. Okay, so that there are different failure theories, right? We'll talk in this in another lecture video, but to understand what is principal stresses, okay? So that we need to find that, right? So for this small circle, we take tensile positive and compression negative, right? And for the normal stresses, right? For normal stresses, we take tensile positive, right? And for shear, we take clockwise shear is positive and anti-clockwise shear is negative, okay? And another important, if you draw a theta here, so let's say for this element, you can see it's tension and anti-clockwise shear. So you can see tension, that's why it is positive on this sigma axis. So this is sigma axis and this is tau axis, normal stress, okay? And this is shear stress, okay? We usually call it sigma, okay? No need to put n. So this is positive and but the shear is negative, so that you have the point here. Here it was still positive tension, right? We don't know, this might be sometimes larger. Let's assume sigma y is less than sigma x, okay? If it is larger than sigma x, it will probably be here, okay? So sigma y is now here, and on sigma y you have clockwise shear, right? So your point is like this, okay? So you can construct the Mohr circle, and let's say, okay, this is not actually the uh, yes, yes. So if you need to know a stress on a plane, right, where angled from this face, it is angled theta, right? We need to know the stresses on this plane, right? So this is sigma theta and tau theta. So in Mohr circle, you can see, right? This is the point on this plane, right? This is the point on this plane. So you can see the angle in between these 2 points is 180, but the real angle between these two planes is 90. So that means you have double the angles, double the actual angles when it comes to Mohr circle. So that means if Mohr circle gives you 2 theta, that's actually theta in the real element, right? So vice versa, if you need the stresses in an element which is theta angle from this face, so that is theta is taken from clockwise direction, right? So that means this is the stress, right? So this is on, you are on this plane, right? You are on this plane. Okay, so this is the point. So you need to go theta. In the Mohr circle, you have to go 2 theta, right? Theta will be given to you, don't worry. Sometimes 2 theta will end here. That's not a case. Theta will be given to you in that case, right? If it is theta is 30, you have to go 60 in the Mohr circle and determine from the geometry. Usually, when you have known points, let's say this is AB, this is CD. You know these points, right? You locate those points and you can take from simple geometry the center of the Mohr circle. That's going to be the x coordinate is going to be a plus b, a plus c divided by, so both will be, I think the height is same, right? AC, let's say AC, this is b. Okay, so the x coordinate will be a plus b over 2. It is from the geometry, right? A circle, right? When you, this is a similar triangle, right? That's why similar triangle. So you can take the height a1, right? So if this is h1, right? So if this is L, right? So you can take this L, right? This is also L, right? Same, right? So, and this height is also H, right? From using similar triangles, you can find this is A plus BO2, and this, since this is on the sigma axis, the y coordinate is 0, right? Okay. So even you can take from this, because actually this will be negative C, this will be positive C. So when you add these two, this is actually C plus minus C over 2, right? C plus minus C over 2. So that's going to be 0, this x comma 0 something, right? So in such case, you can find stresses. And how to find the principal stresses? So principal stresses, so let me erase everything, right? So principal stresses are the stresses on a plane where the shear stresses are 0. So you need to find the stress state where the shear stresses are 0. So that means you have only 2 points. This one is the first, sigma 1. So we take sigma 1 tensile positive. So this is a tension, right? Shear stress is 0. You are on the x-axis, right? And here you have the sigma 2. That means the principal minimum stress, minimum principal stress, right? It's a compression. It's in the negative side. If you have the circle like this, oh, holy shit. let's say your circle is like this. So that means your minimum principal stress is this, and it's also a tension, right? So we need to find this, right? We need to find these two, right? So these are the principal stresses. So how do we find this? So still we can use the geometry, right? So we know this is R, right? So even if you rotate this angle, it is going to be R. This radius is not going to change. This is also R. So if you know this point, let's say there is a D, comma 0. So sigma 1 can be obtained by D plus R, right? Sigma 2 can be taken D minus R. You reduce a radius from the center, right? So you can see between the maximum shear stress is, this is tau max, that is the radius of the Mohr circle, right? So even you can find how much do I, so let's say this, if you find this theta, so this is the theta you need to, let's say this is alpha. So you are on this plane, right? Please pay the attention, right? You are now on this point. So that means you are on this plane. So you are going in clockwise direction to alpha. You find the principal plane, right? And similarly, you are going to alpha from this one, right? Because these two are similar, right? Sorry, alpha, and you find the minimum principal stress, right? So that means from this one you go to alpha in clockwise direction, alpha in clockwise direction, so that you have to go alpha by 2 in the real element, right? And there you will find, so it's a compression tension, so you will find a tension, shear stresses are 0. And from this element, right, from this element you will have to go in clockwise direction alpha by 2 to find the minimum principal stress. So now it's a compression. So actually you have to rotate this element like this by how much? Alpha by 2, right? You rotate in this in the same axis, so it's like this, okay? When you rotate it, you can't place it, translate the element. I draw you to show the show how it's drawn, right? So this will be your, this is the state, right? When you rotate your element like this, so you will have the maximum principal stresses, right? Shear stresses are 0. This is on this plane, you have pure tension, yeah, you have pure compression on this element, on this phase, right? And you can see this, right? Any shear stress you can take from this, right? So that's very easy. So Mohr circle is a graphical method and it's very easy actually. So even this tau max is the radius I show you, right? Even it is equal to this, right? Sigma 1 minus sigma 2 will give you this length, and it is divided by 2 give you the R value, radius, that is equal to tau max, right? So even from that also you can take that, right? So in 3D analysis, you will have, let's say, different plane. In early elements, you will only mostly you will be talking about 2D plane stress conditions, so that you will have stresses on one plane, right? So you are looking from this, right? So this is your I. This was your earlier case. And you have in-plane stresses, but your out-of-plane stresses at earlier case are were zero, right? So that you don't have to worry about 3D. Now you have 3D as well. So we have bit different. So earlier you have X, Y, Z, but your X is now this, right? So you can see you have several components, and you know the shear is complementary and it is in equilibrium with each couple, right? So these two are equal. So you actually have 6 unknowns, right? Even if there are 9 components, 6 unknowns are there only, right? Okay, so six components, right? Not unknowns, because this will be given for you to solve this, right? So, and these are the normal stress. So that now you need to find if there can be stresses in out of plane directions as well, out of plane stresses as well, right? So for instance, we consider XY plane. So XY plane will give you an element plane like this, right? So think about this plane, right? So that will be rotated something like this to have the principal stresses, right? Now this is in 3D, right? And think about X and Z axis, X and Z axis. So you will have an element like this, right? So that will be rotated or stretched out, something like that, right? So we can still use the same principle in Mohr circle and solve it on 2D and assemble that, right? And for instance, the other axis, what's that? That's ZY axis, right? Like this element, right? So what we basically do is we take each plane by plane and draw the Mohr circle and assemble those things, right? Just like we did in 2D, right? And then we can find at which state. So this is not a 2D two-dimensional rotation, right? This is 3-dimensional. You are rotating in this way as well as rotating in that way, right? Rotating in this way and rotating about this axis, right? Guys, you have rotating about y-axis, rotating about x-axis, right? Rotating about the z-axis, so that again you will find a 3 set of angles. I'll discuss you in the previous video. Check that video in 3D stresses, which I did earlier, right? So in my channel, right? So you will find an state where you will get the principal stresses, where you will have on each phase only a normal stress and shear stresses are vanished, zero. To find that, I taught you how to solve this, right? How to take this. So these are called stress invariants, right? These are not, so you can see it's not dependent on the theta. So that means these are independent from your rotations, right? Whatever the values you plug, you will get whatever the theta values you plug. It depends on, it not, does not depend on theta, right? So this was the determinant of the original stress tensor, right? So I discussed this in detail in the previous video. You can check that, right? I will link in the description, right? Link will be in the description. For that introduction, you need that to understand this, right? How these concepts are working, right? So in 3D analysis, so we'll draw an example probably. So you will have some, say, so let's say this is one plane, right? Let's say this is X and Y plane, and let's say this is for X and Z plane, and let's say that will automatically draw the Y and Z plane. So you can see this is the absolute shear maximum, right? So this will give you some maximum shear stress. This will give you some maximum shear stress. You can see the absolute maximum is this one, right? The big circle, right? You have to find the absolute maximum. We usually call, we take sigma 1 is the largest, and sigma 2 second, and sigma 3 is the minimum principal stress, right? We usually order in that way. In that case, sigma 1, you can still hold that sigma 1 plus this one, right? It becomes 3 now, right? Sigma 1. This is the radius of the big circle, right? R naught. R naught. And that's the absolute maximum shear stress, right? So we'll do a 2D problem, right? So please pay attention, right? So this stress is given to you, right? This Q. So don't worry on the plane. So it's give you ZY. So we will work on ZY. But on the x-axis, you don't have any out of plane stresses or shear stresses. So anything, right? So that probably you have plane stress condition. You can still work on 2D. The out of plane stresses are 0, right? So you can work on an element like this, right? So I take that element and you have compression on this face and tension on this face, right? Clockwise shear on this face and anti-clockwise shear on this place. So you know shear is complementary. How to mark on that face? The other face is these two make a couple, you remember. So if this is clockwise, this is also clockwise. If this is anti-clockwise, this is also anti-clockwise. These two make another couple, that is like this couple. The couple making by this, about this, right? You can see the lever arm is, so it will make another couple similar to that, so that these shear stresses are equal, because the element should be in equilibrium. That's why we call shear is complementary. This is called the complementary shear stress, right? If this is tau x, this is also tau x, right? Otherwise the element cannot be in equilibrium, right? So we usually don't need that to draw the Mohr circle, right? So in this phase, right, in this vertical phase, let's say A, let's say that phase is A, this phase is B, right? On A you have 30 and 70, so that means 30 tension and anti-clockwise shear of 70. So you have to mark it. Let's say this is 30. You have minus 70. So this is sigma. This is tau. So, and on the other face, you have compression of 120 and clockwise shear of 70. So the compression, let's say 30, minus 60, minus 90, minus 120, and say minus 120 plus 70, because the shear is clockwise. Here, the tensile blood, but the shear is anti-clockwise. So you know these elements, this element is 90 degrees, right? So that what will happen? So between these two, you will have 180 degrees angle, right? In the Mohr circle. Anything in the element will be doubled in the Mohr circle, any angle, right? So if it is 180, this is the diameter of this circle, right? So you can find the center, right? So you just need to add these two together and divide it by 2. Minus 120 plus 30 divided by 2, comma, that's the x coordinate. This is 70 minus 70 divided by 2, that is 0, right? So this will give you 90 or 2, so that is minus 45, 0, right? So this is 45. Okay. So now I need to find the principal stresses sigma 1. Sigma 1, sigma 2, right? So you remember sigma 1 is, this is r, right? This is the radius. So you can find easily the radius. So this is a straight line. So if you know the coordinates, so again, the same principle, you can find the distance. You take the difference in x coordinates and square it and edit the difference between y coordinates square. So that means you can find, it's Pythagoras theorem, right? It's going to be whatever you add first, that's okay. Minus 30 and this is going to be 0 minus 70 square. So the root of that will be the radius, right? So again, place the difference between x coordinate, it's minus 45, 30. You take 45 first, or else if you take 30 first, you have to take minus 70 first. Okay, for this one as well. Whatever you take first, you have to take it for the other case as well, right? So keep this in mind because this is a square term, so that won't change any effect. But this is very crucial when you find the angle, right? You can find the angle, right? 2 theta by this triangle, right? It's a right angle triangle. This is y over x. So y will be this and 2 theta will be there, right? So you know the height. This is the height. This is the length. So this will this is the diagonal. So that diagonal length is the radius, right? So the radius will be given by the answer is, I think, 102.6, right? You can find this 2 theta, right? So even from sine theta also you can find what is x. So sine theta is not sine theta. Yes, sine theta. Sine theta is now y over r. So that's going to be the magnitude of this. So let's say the triangle is this. So your theta is this. So your y is now, the magnitude of that length is 70, right? This is 0, this is 70. The magnitude is 70, not negative, okay? Because we are taking a simple triangle. So, and sine theta, and then radius is 102.6. So you can take the sine inverse of this. That will give you 7 over 102.6. So this is 43. Not this is sine 2 theta. So theta is somewhere around 21.5, right? So the maximum principal stress, sigma 1, is going to be this point. Let's say this point minus 45 plus r, right? Plus you have to add the radius. From this point, you have to reduce the radius to find minimum principal stress. So minus 45 plus 102.6. So this will give you something around 57.6. 57.6, and sigma 2 will be minus 45 minus 102.6. That will give you minus 147.6, right? This is 57.6. Sigma 1 and sigma 2. So principal stresses are okay, but you need to know, you need to find the angle. So this is the point A, plane A, this is plane B, right? So plane A and plane B. From plane A, you have to rotate your element 2 theta to find the principal plane. When you go 2 theta, you will find this point. And similarly, when you go 2 theta, you will find this way. You have to go clockwise, right? Right? So that if your element is like this, in the Mohr circle, you have to go 2 theta. And in the real element, you have to go theta, right? Remember, this is the theta you have to draw, because why? Mohr circle give you double times the real angle in the element, right? So in the Mohr circle, you have to go 2 theta to find the principal plane, and in the real element, you have to go single theta. That's why we usually use 2 theta for everywhere rather than theta, right? If you use right, so 43, so you have to go 21. You have to angle it 21.21 means something like this. So now you have stresses like this 30 and anti-clockwise shear, clockwise shear, and compression, right? This is 30, 70, and 120. This is 120, right? So you can see when you rotate the element like this, so you will have something like this. A plane where your normal stress on this plane, plane A, this is A, this is B, right? On plane A, right? Let's say A dash, B dash, because it's not actually the same plane, right? You have rotated. So you have 57.6 and minus 147.6. That is tension. Shear stresses are 0, right? I didn't draw that part. If you want, you can draw these two walls as well. So this is in a compression 147.6. So you can see if you rotate it 21.5, right? So your maximum principal stress state is achieved, right? So you can see this is larger than this 57 point is larger than this tensile stress, and 147.6 is larger than this compression, right? And actually there's a plane where you have this kind of stress, right? So in order to find this, right, we use the Mohr circle, right? That means there's a plane, right? There's a plane in this element, right, which undergoes pure compression and pure tension, right, larger than these values. So we actually can take that plane as this, something like this, right? So this kind of a plane, right? So if you draw it in this way, so that will look like this. I will draw it. So you are this plane you have to, so rotate it 21. This kind of a plane, right? This kind of a plane is there for you to find the maximum normal stress, but still it's 2D, right? Let's say what will happen in 3D case. So I think you understand. So the maximum shear stress is also this. It's the radius. So radius is again 102.6. So other things are okay, right? So you can go ahead and let's do a problem like this, 3D, right? So it shows you a cylindrical pressure with a wall thickness of 6.25 outer radius and 100 millimeter radius is filled with gas, and measured pressure gauge inside tank is 200 kilopascal, right? That means 2 megapascal, right? So find the absolute maximum shear stress at point A, right? Let's say this is point A. You take an element, right? So that element, so this is your pressure cylinder, right? So since the entire vessel is closed, right? So that pressure try to push these walls in this way and that way, normal to the, so pressure is, normal to the surface, right? Whatever acting. So that means, so if you take an A element like this, right? A element like this, so that thickness, this is the thickness of the wall, right? So this try to push this lid in this way, so that, so this try to push this, so that means it will exert the exact, because it is resisted by this wall, right? So that means it pulls this wall as well. When lid try to go away, right, it pulls this wall as well, so that you will have this kind of a stress as well in this element, and as well as stress out of this plane, right? So it will sorry, not out. So this out of plane stress, actually this, so this pushes in this way, right? Pushes in this way, right? So pressure is acting on perpendicularly, right? So what actually that pressure does, right? Think about that. So it try to push, right? So let's say this is the uh, original wall, right? So it try to push this way. So that means, right? So what happens is, so this is not the stress on this element, it try to push it. This is the stress along that element in axial direction, right? So this is the axial stress, right? Right. So that will be occurring in this way. It try to push this wall, right? Sorry, pull this wall, right? So even an element will be subjected to that stress, right? Small element. So what if we try to push it, right? So it try to, what happens? It try to be large, right? So try to be large means this wall try to what? Expand, right? This wall try to expand. So that means this try to, if an element is there, is element is pushed, sorry, pulled outward, stretched, right? Right, due to this pressure, right? Right. So we try to push this wall, right, from everywhere to perpendicularly, right? But it can't actually push, so that it will have a stress like this, right? To what? So this is a in plane stress, right? In other terms, the membrane action, right? In plane stressors are developed, right? Right. No out of plane action, right? This is pure membrane, right? Membrane action, right? Membrane stressors are there, right? Membrane means the in plane stressors, right? No out of plane stressors, but this is the P, right? P try to push this. That means due to that, right? Due to that, so this is the wall we were talking about, right? It try to push this way, right? Try to push this way, the element. So this is the section we are talking about. Let me draw it again. So if you have some element, right? So this is thickness, right? Let's talk about that element, small element, right? So that means it will have stress components. This is along the circumference, right? Circumference, right? Circumference. So, right, try to stretch, and this is axial direction, right? I think you can't see this, right? Right. So this is kind of an element that we have, right? So you can just define some axis, define a small element even closer than a cube, and take these are the stresses acting, right? So since this pressure is always perpendicular, right? So you can expect what? So anyway, this is on axial stress. So this this pressure is normal, right? So that you can expect normal stresses, only normal stresses, right? So you don't have out of plane stress, right? So pressure is acting out of plane, right? Acting on out of plane, but it actually triggers this membrane action, right? It resists the pressure, try to push this, right? Try to push this, right? So that this will try to stretch, right? This element will try to stretch, right? So that you will have something like this membrane force, right? Membrane stress, right? Actually, so and you know these things, right? So we call the circumference stress is hoop stress, right? Sigma h, and this is axial stress, right? Axial direction. So hoop stress, right? It's, we call it the along the ring, right? Right. So let's draw that element, right? So this is the axial stress, so I call it x-axis. Okay, so the sigma x was there, right? So this is y-axis, right? So if you take a small element, sigma y will be there, right? And this is the z direction, you don't have anything, right? This is resisted by the membrane stresses, right? In plane stresses, no out of planes. But there can be a plane or an element configuration, right? Where you can have, right, the sigma 3 as well. Or as let's say, not sigma 3 actually. So how do I say that? So let's say you need to know the absolute maximum shear stress, right? So that's your task, right? Don't worry about the, for now, the principal stresses. In the previous example I did, in the previous video, I did how to find the principal stresses. So in this case, you have to actually, the objective is for you to find the absolute maximum shear stress at point A. So that you need to draw this on a Mohr circle, and to that you have to find this stress, right? So you know the hoop stress is given by this equation, PA over what? PR over PR over T, and this is PR over 2T. And you have to check this R by T, sorry, T by R ratio, okay? There's some number. If that, if it is less than that number, you can use this, because we are usually deriving this for thin walls, right? Thin walls, okay? So where we assume that through thickness stresses are negligible, right? Okay, so in such case, if you use this, so you have P is 2 megapascal, that means 2000 kilopascal, and This is R and this is T, right? So you can find this PR over T. So what's that? 2, that's megapascal. R is 100 over T. What's 6.25? This is 2, sorry, R over T, right? No, sorry. P over PR over 2T. So simply divide this by 2, right? So that's going to give you 200 over 6.25. So that's going to give a value of 32. Right. So this is going to give you a value of 60, right? Okay. So yes, we are done. And radius is done. Okay. Now we don't know sigma. Yeah, sigma z is 0, right? Okay. So that you can find you can draw the Mohr circles because you know no stresses along the thickness direction, right? In this way. Okay, so can draw this. So if there are no shear stresses, so these becomes the principal stresses. So we actually draw it on the sigma axis. This is 32. This is 16, and this is 0. Is 2, right? For this plane, 16 and 13, for this plane, right? Y-X plane, so this is the Mohr circle. Because we are having this principal stresses directly where the planes shear stresses are 0, right? So this is the Mohr circle, right? And for X and Z, you have this plane, right? Right? So X and Z, so that means 0 and 60. So this is your Mohr circle, right? Because actually how you point this one is your shear stress is 0. So 16, coordinate is 16, 0. Coordinate is 32, 0. Shear stress, normal stress is 32. Shear stress is 0. See, when the shear stress is 0, your normal stress becomes the principal stress, right? So in such case, you will arrange sigma 1 is the largest and sigma 3 is the lowest, okay? So let's say, so for 0 and 32, for this plane, y z, you can draw the Mohr circle like this, 0 and 32. So you can see this is sigma 1, this is sigma 3, lowest principal stress, this is then sigma 2. So your absolute maximum will be given by what? Sigma 1 minus sigma 3 divided by 2. or else the radius of the bigger circle. Let's say this is R0. Okay, so that will give you 32 minus 0, that's 16, right? So that's your absolute maximum shear stress, not this one, right? You can see this is 16, so this is 8, this radius is 8, this is also radius is 8, right? It's not the absolute maximum shear stress. So along this element you will have the maximum shear stress, but for that you need to rotate this element, right? So now let's check. So if you are on this plane, right, so for y 32, you have to go in clockwise direction. This angle is exactly 90, right? Because we are in the x plane, x axis. So if it is 90, right, if it is 90, you will have to go half of that in the element, right? You have to go half of that in the element, right? So that means your element will look like this. So you have to go 45 degrees, right, to find the maximum maximum shear stress, right? Okay, so that means the entire element has to rotate, right? Because they are in 3D case, I just draw only the plane only. So hope you understand that, right? Okay, so the link for 3D stress intro is in the description, right? So please watch that. Find how to draw these ones, right? Okay, so let's consider if you have some element like this, so the same element, right? Same element, right? Have some stresses, and this will also have some stress, right? So in such case, you can draw this Mohr circle for this plane, right? But on this plane, they have only given the, let's say this is 30, and this is, let's say 50, and this is, let's say 20. Okay, and let's say this is how much? Let's say this is a compression. Okay, let's say this is a compression. On that phase you will only have compression, right? No shear stresses, so that means it directly become the principal stress, right? It directly becomes the principal stress, right, of minus 40, sorry, 40, right? That's anyway minus. Okay, so you can draw this Mohr circle still, right? It's 30, 20, 20 is anti-clockwise shear. Let's say 30 is here, 20 is here. This is 50 and clockwise shear, that's positive. So this is, these two are the points you can. So on that plane you can find the principal stresses, right? Where are your principal? So because these are not the principal stresses on that plane, there is a shear stress. So that means you can angle this element such that there will be a plane in xy. So these are in plane stresses. Okay, this is the out of plane stress. Okay, so you mark out of plane stress. This is 40 and 0, right? Minus 40 and 0. Why? The shear stresses are 0. Again, it's the principal stress, right? Then okay. So from this element, you can find these two values. Sigma 1, this is the maximum one. We call this sigma 2, right? It's just like the 2D case, right? And you mark this minus 40, 0. Somewhere around here, right? This is sigma 3, right? It's minus 40, right? So for sigma 2 and sigma, right, you can draw this small circle. We don't know it is bigger than this or that. Okay, we don't know it. I don't know the value. I didn't calculate. And you have for sigma 3 and sigma 1 along, you have another circle, right? And this will be your absolute maximum shear stress, right? Again, you can find sigma 1 minus sigma 3 divided by, so sigma 1 is positive, right? Anyway, positive. And sigma 3 is originally negative, right? So negative will be plus, right? Plus something. So that should be right. Because this is a compression, this is a tension, right? So likewise, you can work it out. This is the absolute maximum shears. Absolute, right? So even you can rotate these elements, right? So in, let's say this is sigma 1. So in sigma 3, you don't have to rotate the element because it's in the principal direction, right? You can rotate this element in xy in plane, right? In plane such that you can find this. So you can see in this plane. So here you have 30 and so this is A, right? From A, you have to go anti-clockwise direction to find your principal stress. So that means you have to rotate this in anti-clockwise direction to find the principal plane, right? So there will be a plane like this. You have to go, no, in clockwise, right? In clockwise direction, sorry. In clockwise direction, theta, to find the principal stress, right? So this is the corresponding, and if you here, you have to still go anti-clockwise this much. Let's say this is alpha. So that means the original element has to be rotated alpha by 2, right? On x and y plane, right? So xy plane I'm drawing like this. Right? Here it's anyway given the principal stress, right? So you need to rotate this xy plane, right? Then in clockwise direction. So it will be like this U element finally. It is rotated, right? So that you will have sigma 1 in this plane, sigma 2 in this plane, and sigma 3 in this plane, right? So this is the principal orientation, right? Here you need to no need to rotate about this plane because here they have given the principal stress, right? So Now your element on this plane is like this. Right? Right? Hope you understand that. Thank you very much.